Hello, welcome to the third live session of Concept Topology 2 course of NPTEL. This is Shavi. I'm working under Commerce Costing with Matrix. So before starting, let me know whether I'm audible or not, and also let me know whether the screen is visible to you.
Hello, sir.
Yeah, please tell.
I have a little doubt. The
Okay.
previous,
First, could you please confirm that am I audible or not?
yes, you are
And could
audible.
you please confirm that my screen is visible to you or not?
I can.
My screen is visible to you or not?
Yes, yes, your skin is
Okay,
visible.
thank you. Okay, please go ahead.
Can you ex- can you please explain again that why Q is not locally compact?
The last classification. Okay, yeah, and okay, so mm, right. Hmm, sure. So the so what does it mean by so let's first recall the definition of local compact. Okay, so the question is Q is not locally compact. So first of all is like that Q is not set of rationals is not locally compact. Okay. So in order to prove this, you need to go along with the definition. Okay. So what is the definition of local compactness? Local compactness means for every point x, we can get as a compact subspace C at of the set capital X, which contains a neighborhood of x. Okay. So if Q is locally compact, then choose x naught belongs to Q. Then there exists a compact subspace C of Q which contains a neighborhood of x. Correct? Till now is this clear? It is not it is nothing but the just elaboration of the definition, right? So this means what? So x belongs to some open interval intersection Q under subspace topology, which is subset of C. Okay, this is x naught. Okay. And remember, C is compact. Okay. Now, yeah. So now, what we can do is the following. So now, wait a minute. Now choose a sequence xn in open AB intersection Q such that xn goes to some irrational numbers. Call it y. So what are we doing? We are choosing a sequence xn from the open interval AB intersection Q such that xn goes to some irrational number. Okay. Call it y. And why it is possible? It is possible due to density property. Okay. Now, since C is compact, so C closed also. C closed as Q is Hausdorff and C compact, which is by choice. Okay. So this implies what? This implies that since that sequence xn, this term belongs to open AB intersection Q subset of C, this implies what? This implies Y belongs to C. It is subset of Q. But it's a contradiction, right? Why? Because Y by choice is irrational number. So that is the argument. So let me repeat the argument. So if we suppose assume Q is locally compact, okay, means what? This compact subset C of Q, which contains a neighborhood of X, correct? So there exists an X naught. So I mean, so if we choose any point X naught, so that X naught belongs to open AB intersection Q subset of capital C. Now choose a sequence Xn and open AB intersection Q, so the Xn goes to some irrational number, call it Y. So now since C is closed and Q is Hausdorff, I mean C is closed because Q is Hausdorff and C is compact, and closed subspace a compact. I mean compact subspace a Hausdorff is closed always, right? So that's why C is closed. Okay. So now since the sequence Xn is lies in capital C, and since Xn goes to Y, so Y will belongs to capital C, but capital C is a subset of Q. But that's not possible because I mean that's a contradiction because by our choice the little y is an irrational number. So that's why Q is not locally compact. So this is the argument. Are you able to understand this? Let me know. Are you able to understand this?
Hello, sir.
Yeah, please tell me.
In the previous class, you proved that.
Okay, before going to the previous class, could you please confirm whether you are able to understand this solution or not?
Yes, yes, I can.
Okay,
I
yeah,
understand.
please go ahead.
In the previous class, you proved that cofinite topology in always not compact, while
Yeah,
co-countable is always compact.
correct.
Please, if you because in the
Yeah,
last class, I am not.
yeah. Okay, yeah. So that's not a mistake. So you have so there are two questions. First one is co-finite topology is not compact, but co-counter topology is always compact. Those are the two questions. Okay, so well let me go one by one. Okay, so first question, co-finite topology. So the statement correct is as follows: co-finite topology on infinite set. Okay, I mean infinite set on infinite set, co-finite topology only makes sense. Otherwise, it has no sense. Okay, that's the point. Cofinite topology infinite set is always compact. So how that's possible? So so before writing the solution, let me tell it very straightforward that this solution is easy, but this is not direct. It is a quite tricky argument. So you need to practice this type of things more and more in order to get good marks in exams. Okay, because finally exams matter. Exams are the thing which matters. Okay, so that's the thing. So okay, so let's get back to the state of business. So let capital X be an infinite set with cofinite topology. We want to show capital X is in capital X is compact. So choose choose what? So what we need to choose? We need to choose open cover. E all for capital X. Okay. So now choose alpha naught from the index set. Now since U alpha naught open in X, so X minus U alpha naught is a finite set, correct? But X infinite, so U alpha naught infinite. Anyway, leave it. This doesn't matter. Sorry, I mean only we need to use the fact that X minus a finite. That is what only we need to use. Okay. So now, so let x1, x2, xn is equal to x minus u alpha. Correct. Now, so choose alpha 1, alpha 2, alpha n such that xi belongs to u alpha. Correct. So this implies what? X equal to u alpha naught, u alpha 1, dot u alpha n. So this open cover u alpha admits finite subgroup. So this is a so that's why it is always compact. So what we have done, kind of a minute, please. So what we have done. So basically, we start with an infinite set. Okay. So capital X, and then we choose an open covered U alpha of capital X. Okay. Now we are choosing index set alpha naught. Now since U alpha naught is open, so X minus U alpha finite set. Now, so X minus U alpha finite set. So rest of the post infinite. So suppose x1, x2, xn equal to x minus u alpha. Now we are choosing alpha 1, alpha 2 alpha such that xi belongs to u alpha. So this implies capital X equal to u alpha 1 dot not dot, u alpha n. So that u alpha n is a finite subgroup. So that is the thing. Okay. So this is the argument. Yeah, it's quite tricky, but it's not complicated. So Mustaq, let me know whether are you able to understand this argument or not.
Yes, I understand.
Okay. So now regarding the second question, um, okay. So now regarding the second question, uh, so yeah, so what are the second question? I forgot actually. What is the second question, Mustaq? Mustaq, what a second question. Ah, okay. So your second question was the following. Yeah, I can remember. So co-countable topology on uncountable sets. One place. Yeah, sorry. So your question, second question was co-countable topology on uncountable sets is not compact. So how to do it? So the process is the following. So let capital X be n. Uh, Firstly, well, it's tricky. Okay, so you need to revise this. So suppose capital X uncountable set with co-countable. Okay. We need to share the compromise. What means we need to construct an open cover which does not have the finite subcover, right? Correct. So in order to construct an open cover, we're going to use a special trick. This trick goes as follows: choose an countable set x1, x2, x3 dot 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 subset capital. Okay. Now define u1 x minus x2, x3, x4 dot u2 x minus x3, x4, e3 is equal to x minus x4, sorry, and so on. Okay. So first of all, clearly these UIs are these UIs forms an open cover of catalyst, correct? But it does not admit finite support. Why? Because if x equal to ui1 union uin, then define m is equal to maximum of I1 I2 I, and then this xm does not belongs to the union of ui of ij, which is equal to 1 to n. So that is a contradiction. So co-countable topology, it cannot be compact or uncountable set. Now Mustaq, let me know are able to understand this or not.
Yes, yes, I
So
understand.
Do you have any more questions?
No.
Oh, so wait, kindly wait for 2 minutes. Uh, let me open my notes. Kindly wait for 2 minutes. Kindly wait for 2 minutes. Okay. So, okay. So now, um, okay. So now today we shall continue with the countable action. Okay. So, one. So, countable action. So there are two things. One is countable axiom, another is separation axioms. Okay. So today we shall first start with countable axiom, and of course I hope that today we'll have a time to go for separation axiom and possibly problems, possibly solve the problems. Well, let's see how much we can do today. Okay. So this one is countable actions. So there are two things. First one is first countable axiom. Second one is second countable axiom. Luckily, those are good ones. So first, let's start the first countable action. So, so let space capital X is said to satisfy the first countability axiom at X if there exists a collection capital of collection of neighbors of X such that each neighborhood of X contains at least one of the elements. Okay. One is so a space capital X, say to the first count by axiom X, if there is a collection beta of neighborhoods of X such that each neighborhood of little x contains at least one of the elements of beta. So this definition, local definition, first contributed axiom at X, and if capital X satisfies first contributed, if capital X satisfies first contributed actions at each point of X, then X is said to be the first countable space. Okay. Then it's the first contributed space. So that is the thing. So let's give some examples. Well, so first one might ask that why this is important at first place. Well, so look, after giving some examples, we look into some properties. So that will be of point of interest for you. Okay, so that's why the first concept is actually a very good example for a space. Okay, I mean if a space is first countable, so it is almost going in the direction of to the metric space, but of course not fully metric space. There are some constraints. Well, let's look into it slowly. So now, so hmm. Let's take some examples. So real length with Euclidean topology is first count. Is first count. Why? So can you please tell why the real and itinerant topologies first going to discuss? Think about it. You can take your time. Let me know. I'm waiting for 2 seconds. Think about it. Why real and satisfy is the first condition. So for that, what you need to ensure? You need to ensure if you choose an arbitrary point from the real line, and you need to get a collection of open subspaces such that if you choose any open set around X, that open set contains any at least one open set from your chosen collection. Sorry, from your constructed collection. So please think about it. Let me know. Yeah, please think about it. Let me know. In the meantime, let me check the possible problems. You can take your time, and if you are able to get any answer, please unmute yourself and let me know. Wow. So, Mr. Are you able to get any solution argument for this? I mean, why Mr. Are you able to get argument for it? Hmm? Okay, no problem. Let me discuss it. So look, so first let me tell it geometrically. Okay, so we have some real line, correct? choose any point x naught here. Okay. Now we are choosing the neighborhood x naught minus 1 by n, x naught plus 1 by n. Okay. And define u and to be that same neighborhood x naught minus 1 by n, x naught plus 1 by n. Okay. So now, suppose let V contains an x naught be an open set. I mean, now what we need to show, we need to show that if we take any open set around x naught, that open set will contain at least one of the events, right? To the other part, correct? So let V belongs to x naught be an open set. Okay. So so obviously what that x minus epsilon, x naught minus epsilon, x naught plus epsilon be a subset of B for some epsilon greater than 0. Now Barker property, choose M a natural number so that this 1 by M less than epsilon. So this implies that x naught minus 1 by M and x naught plus 1 by M, this is a subset of U. So this is what, this is nothing but our U, correct? So this is what actually we want to prove, and this is the desired thing that we have achieved, correct? So that's why, so what? So the real line with usual topology is first counter, correct? So well, so let me repeat the argument. What to make this? Oh, so let me repeat the argument. So what we have done, we have chosen an x naught, and then we have chosen two endpoints x naught minus 1 by n, x naught plus 1 by n. Okay? Now, so my claim is that this collection x naught minus 1 by n, x naught 1 by n this from the our desired collection. For that, we need to do what? We need to choose an open set containing x naught. And now observe that x naught plus epsilon, x naught plus epsilon subset of b. We need, so I mean, because of the open. Now by our equivalent property, choose an little m such that 1 by m is epsilon. Now x naught minus 1 by m x naught plus 1, this thing is subset of capital B. And so this is what? This is actually um. So that x naught belongs to subset of capital. So this is what our desired result, right? So that's why real line usual topology is first count. Okay, that's the thing. Well, so wait for a minute. Let me find some problems possible to do right now or not. Okay, let's hold on. Okay. So now, well, so this is one example. Well, so we will look into other examples soon. So before going to example, let me describe some properties. Okay. So the first thing is the following. So we have some the following here. That x be topology. Suppose a subset of x. Now, if there exists a sequence of points of a converging to x, then x belongs to a closure. And converse holds if x is first countable. The first thing, first and second estimate is the following. Second is let if x to be a map and if is continuous, then for every sequence x in x, the sequence fxn, and this xn converges to x, the sequence fxn converges to fx. Converse, sorry, converse holds if x is first countable. So this is the thing. So please take your time, think about it, and let me know whether you are able to get an idea or not. Please take your time. I shall let me start with after 1 or 2 minutes. Okay. Yeah. Okay. Okay. So before starting, you see that so look, the statements one side is always true, right? So there is nothing special. So the converse is actually point of importance, right? The converse of the both situations first countable whole. So now in metric space we have seen that both side are always true. So basically the metric is the first countable. So we will see soon. Okay, so that's the point. Okay. So so for both side, uh, okay. So both side. So okay. So firstly, for both questions, for both of the statements, one direction is always true and is true. So one direction means for the first question, if x and sequence in x now. So okay. So for first question is that if xn is a sequence converging to x and xn belongs to capital, the x, this thing is okay, I guess, for everybody. Anyway, I'm not going to prove it now. So for the same question, we need to prove. So suppose this is first countable. Okay, for converse. So for converse, uh, let capital X is first count and let x is. We need to show what? To show there exists a sequence xn in A such that xn goes to x. Correct? So this is what we need. So choose uh, countable basis events at x in x. Okay. Now put v1 is equal to e1, v2 is equal to e2 intersection v1, v3 is equal to u3 intersection v2. So then obviously what? Then v1 contains v2 contain uh, v3 dot dot. And clearly this collection vns forms uh, countable sorry forms a countable basis at x. Correct? Now I mean this is the one trick, this is a trick actually. Now since now since x belongs to a closure, so un, so this vn intersection n non-empty for all n. Correct? So choose xi via intersection a for all I. Now claim is this sequence xn goes to x. How to prove this? So for that what we need to do? We need to choose one. So what I need to do? We need to choose NW open source. This implies what? This implies Vn naught subset W x for some x for some n naught. Now Vn's are monotonically decreasing. So here the advantage of choosing the decreasing sequence will play. So this x belongs so Vn subset of W for all m greater than equal to m naught. So these equal to what? Xm belongs to W for all m greater than equal to m. So these sequence xn goes to x as n tending. So that is the thing we want to do, right? So this is we are able to obtain the sequence converges to x. So that is the thing. Now wait. Okay. So what we have done. So basically, so 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 let me repeat that. Okay. So in order, so what is the technique construct in the sequence? So in order to, so we have first choose the counter base un of x at x. Okay? And we put v1 as v1, v2 is equal to u2 intersection v1 and order. So basically our first target is to given the open counter base at x, we are making it monotonic. So, so that is a trick that will be useful later. Now vn is a counter base at x. So it's a base. Now since x belongs to a closure, so vn intersection is non-empty for all. Correct? So we are choosing xi belongs to vi intersection of all. Now we are claiming that xn belongs, xn goes to x. So for that what we can do? We are choosing a w containing little x. Now little x belongs to vn not sub to w for some x. Now since v is monotonically decreasing, so this vm subs to w for all m that equal to m. Here actually this monotonically decreasing is useful. So this is what the xm belongs to for all m greater than equal. So this is the word. Xm goes to x for all m greater than equal to infinity. Goes to infinity. So that is the thing. Okay. So that is the argument. So please think about your friend to have any question or any doubt. I shall wait for one. So let me know, do you have any question or doubt, or else we can proceed for the next thing. Oh, okay, so it seems that there is no confusion and doubt. So now, so let me go for the second proof. The proof goes as follows. So let me. So what's the step? Oh, so the what is the second question? So second question is the following. So the second question is that suppose if the map from x to y is continuous, then for any sequence x in if x goes to f, then so this one is, of course, this one is direct. There is nothing to prove here, so we will prove the converse part. Okay. So converse. That is if for any sequence xn in x which goes to x, fxn goes to fx, then f will be continuous. This is what we need. Okay. So this means what? So for each okay. So in order to prove this, of course we cannot directly open the closed definition. So what we can do? So remember that, recall that if you can remember recall one of the criteria of is continuous is namely the one of the criteria was that f of a closure subset of f of a. So this is one of the criteria that we will use. Okay. So we are doing what? So let y belongs to f of a closure. This implies what? Y is equal to fx for some x. Now since x is first countable, so there exists a sequence xn in capital A such that xn goes to, then the given condition tells f of xn goes to f of x, and of course xn goes to A, so xn belongs to A, so f of xn, this thing belongs to f of x. So these two things is what? These two things give f of x belongs to f of a closure. So this implies what? This implies y belongs to f of a closure. This implies what? This implies f is continuous. So this is argument. So think about it. Let me know as a back after 3 4 minutes. Okay. So, uh, okay. So let me know. Are you able to understand this argument? So let me know. Are you understand? Will this understand the argument is not? Okay. No. Okay. So anyways, let me repeat the argument again. The argument goes as follows. Let me ask what argument is.
Hello, sir.
Yeah. Please tell me.
Sir, can you please tell me uh, why we need this type of countability axioms? Well, or actually, what is the advantage of this countability axioms?
That's a very good question. So, as before, I've already told. Let me repeat. Look, what else? Let me bring up the question. Yeah, yeah. So you can see those two theorems on the screen. Correct. Now the point is that in case of metric space, these two theorems are true. You have seen, I hope. But in case of topological space, these theorems are not true in general. So whenever a space is first countable, so we can, I mean, so if a space is first countable, so on that space, most of the properties of the matrix space holds. For example, in continuity, you can say that xn if xn goes to x, if xn goes to x, f is continuous. For case of definition of closure, xn goes to a for all xn goes to x, and if xn belongs to a, then x belongs to x closure. So these are the statements that are valid on the first countable space. So that's why a first countable space is a topological space, which is almost a metric space, but of course there is some property which will not satisfy. So it is nearer to the metric space, so it behaves in a very good way. So it's very easy to deal with this type of spaces as the first countable action. So that's why these are of point of interest for many people. So that is the only reason. Okay. You understand my point?
Yes,
Oh. Okay, so Musta, tell me, this last argument where the xn goes to x, xn goes to x into this is continuous. Are you able to understand this argument properly or not? Let me know.
yes.
Oh, thank you. Okay. Oh, anyway, so let me repeat the argument once again because it's quite tricky. So, so, so basically what? So we need to prove that f of a close subset of f of a. This is what we need to prove. Correct? In order to shape this. Now, since y belongs to f of a closure, so y is left for some equals to a closure. Now, since x is first countable, so there exists a sequence xn in capital S such that xn belongs to a. And the given condition tells that fxn goes to fx, right? And fxn goes to f of x. Now, since given condition is what? Since x is first countable, that is first countable. Fxn goes to, and since fxn goes to f of x, this implies fx belongs to f of x. These implies what? These implies y belongs to f of x plus these implies f is continuous. Okay. So that this is what we want. So now So now, so this is all our first so in the first countable axiom, two things hold, namely if a sequence extend in capital S as the extend goes to X goes to A closure, and the second thing is the continuity converse the continuity is also true. That is the thing. So now let's go back to the countability axiom again. So this is all about the first countability. So before, I mean, so well, there are some many examples, but before going to examples, let's dive into the second countability axiom. Okay. So the second countability axiom. So definition is that a space capital X is said to be said to be second countable if it has countable basis for its topology. Okay. So so this means what? So this means it's just let me clarify what does it mean by basis for its topology. Okay. So this is one thing is need to be clarified clearly. So basis for its topology is what? Suppose tau be the topology, okay, and suppose B is the basis for its topology. Means what? Means if we take any open set inside topology, and if we take any point belongs to U, so there is this time basis element B inside the capital. So that does, so it means, so this is what it means, basis for its topology. It means that this basis generates the same topology as the given topology. Okay. So the space is second counter, you can countable basis for its topology. The countable basis, that's the second countable action. Okay, this is one. Now there is a theorem, namely wait a minute please. Okay. Now, so first theorem is that the second countable implies first count. Actually, it's a very natural question to ask, but anyway, it's a theorem because this is what it is. Okay. So second implies first countable is what? For first countable, we need what? We need I mean, around each point we need to take a countable collection of open sets, right? So how to get that? So choose x belongs to x. Okay. And suppose beta be countable basis for its topology. Okay. Now choose beta prime contains those elements capital beta such that x belongs to. Okay. Now claim this will work for the first countable index, for first countable index of x. So for that, what we need to do? For that, we need to choose an open set containing x. So these will work because due to basis b x belongs to b naught subset of b for some b naught belongs to basis. So these similar this b naught belongs to b plus and satisfies b naught subset. So this is the so b naught satisfy that property. So this is what we want to do, correct? So think about it. Let me know. Do you have any question or a doubt? Start from the construction itself. So now, so of course, so what? So one may ask what the converse. So of course, converse not. That is, we need to find example of space which is first counter but second counter. So so consider that is real line with lower limit topology. Okay, it is first countable but not second. Question is why. So let's get to first countable. So we are taking so look. So let's try to understand geometrical. So we have this real line, correct? So choose an x naught. Now this is x naught and this is x naught plus 1 by n. So if we define un to be x naught plus x naught 1 by n, these are open in low limit topology. And clearly if x naught belongs to Vn be open, this means what? X naught belongs to obviously x naught comma x naught plus 1 by m subset of phi for some m. So oh so so this tells that R with lower limit topology is first count. Now we need to show that is second countable not correct. So it is not said. So claim is so this first countable is done. Okay. Now the R with lower limit topology is not second countable. Suppose yes. Suppose it is. So then then let beta be a basis which is countable, which is this countability is important for its topology. Okay. Now x belongs to x comma x plus 1. So this implies what? X belongs to n subset of x comma x plus 1 by n. So this implies what? This implies infimum of beta n is equal to x. So this implies what? This implies if it is point x not y, then dx not equal to dy. Correct. So this implies this collection beta is uncountable as yeah. So that is the thing. So let me repeat the argument. So oh well. So so the thing is the following. Okay. So basically, so if beta is a countable basis for its topology, his countability is important. Okay. So now since x belongs to closed interval x comma x plus 1 by n, so this x belongs to Bn. Subset of x comma x plus 1 by n. So these implies the infimum of Bn is capital X. So this implies what? For each x, for each distinct x, Bx not equal to Bn. So this set capital B is uncountable. So that is the contradiction, right? So that's why. So R through all limit topology is not same countable. That's true. Okay. Now, so this is the thing. So well, so these are some properties. Now, second countable axioms give rise to some two beautiful properties. Namely, so before that there are some definitions. A space X capital X is said to be Lindelof if every open cover has countable. So basically, compactness is a strong conditional linear. So linear limit implies every open but countable subset. Linear. And second property is separable. A space is said to be separable if separable if each has a countable dense subset. So there are two things. So for example, Q is separable and the linear examples. We will see the examples. Right now, giving example is not possible. Now there is theorems. So every second countable space is linear and separable. So right now the this linearness portion the we will this proof we will see after in the next session. This proof latter only proof for separability. So 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 basically we need to prove that it is a countable dense subset, right? The countability and dense will show. Correct. So so choose x belongs to x. Okay. So for each basis element, I mean, so this be the be countable, this be the countable basis. So for each basis element Bn, okay, So for each bn choose, we are can choose xn belongs to bs. Correct? Sorry, this bn. Okay. And define d to be these actions. Now claim is that this d closure equal to x. That is d is dense in x. This is what we need to do. Okay. So d is dense in x. How to do? So this is what. So now choose. So for in order to do so, we need to take. So that is now for u being open set in x. Okay. So basically every point in x and every basis element containing x intersects t. So this x belongs to t. So that is the thing. Okay. So that's why it is separable. So basically is we can choose a collection B. We can there is a collection Bn, and for each video we can do a point, and those collection of the points we call it D, then D is just that's all. Okay. There is nothing. I mean there is it is nothing complicated. Uh, oh. Oh, oh, okay. So that's the thing. Okay. So now, okay. So that's why second counter is separable. So okay, so there is a Lindelof condition we will see in later, but right now we are not going to prove this. So right now what we're going to prove is the following. So there are some facts. So uh, the fact is the following. Okay. So of course one may ask that does Lindelof separable implies second counter? Of course the answer is not. Of course. So what is the example? So the example is R of lower limit topology. It is Lindelof plus, but not so all. Okay, so let me tell you clearly. This is basically this sessions are basically problem solving session. If you have any doubt, any question, please let me know. Or if any problem understanding this session, please let me know. This problem is basically clearing doubts. Okay, so please do utilize these sessions cleverly. Okay.
Rosette,
Yeah, please tell Mustafa.
can you please repeat why lower limit topology not Lindelof?
Sorry. Could you please repeat your question? I am unable to get. Please repeat your question.
Can you please repeat why lower limit topology is not Lindelof?
Uh, well, so so the thing is that the lower limit topology is not is Lindelof. Actually, that's what I'm going to say after few seconds. The point is, there is separate proof for that, and it requires a lot of work. Now today it is not possible. So this proof we will see in the next session. But for the timing, remember dual topology is possibly one of the few examples where this Lindelof. I'm sorry. First of all, lower limit topology Lindelof is requires a lot of okay, and it is separable because that's uh, that rational set of rationals inside. These are separable. Okay, there is no harm on it, and it is not second countable. We have already seen. The Lindelof effect we will see in the next session. Today, this time is too short to continue for the Lindelof. Okay, but keep this example in mind. On next session, please give me a reminder. I will prove it. And also remember the example for exam purpose. Okay, that is the thing. Anyway, that's the problem. So anyway, the exam is after many months, so there's no point thinking about that. Okay, so okay, so there are only few minutes left, I guess. Let me check. Okay, so there are a few minutes left. So if you have, yeah, sorry. So if you have any question, please ask. I mean, within 2 minutes, in this 2 minutes, there is nothing we can prove nothing actually. So if you have any question, please ask. So on the next session, what we will do is the following. Next session, we will prove that lower limit topology is Lindelof. Second, product of Lindelof space is not Lindelof. So this is one thing. And subspace of Lindelof is not Lindelof. Sorry. Yeah. So possibly these are the things, and also second countable in plus Lindelof. So these are the few things that we will prove in the next session. So for today, also these are the things for today. If you have any doubt, please drop an email over the forum. I shall try to reply it as much as I can, or else if I am not possible to reply at the moment, I shall solve the question on the next session. Okay. So that's all for today.
Thank
Uh,
you.
Thank you for joining the class. We shall meet in next session. Thank you. I'm leaving the call.